now we'll start Unit 2, which has got two sections. The first one is section 4.3, dual spaces, and the second one is section 4.4, inner product spaces. So in this first we have the lemma 4.3.1, which states that if V and W are vector spaces over F, then whom W is a vector space over F. This we have proved in result 4.1.14 and section 4.1. So we consider this whom W, defined the two operations addition and scalar multiplication pointwise, and established that that is a vector space over F. Now in the next theorem that we are going to prove that if V and W are of dimensions m and n respectively, then whom W is of dimension m into n. Now since V and W are vector spaces over F of dimensions m and n, we can have V1 to Vm to be a basis of V and W1 to Wn to be a basis of W. Now before we actually prove the theorem, in order to establish the equality of two mappings, see, we know that equality of two mappings can be achieved by showing that their images are equal. For the mappings to be equal, we need to have the images to be equal. This is known to us already. But now as homomorphisms, and homomorphism defined on from a vector space of finite dimension to another finite dimension vector space. So in that case, instead of having it for general V in capital V, it is enough we have that they agree on basis elements. So instead of considering general element V, it is enough I consider the basis elements. If they agree on, if both the homomorphisms agree on the basis elements, then we can have the homomorphisms to be equal. So that is what this result says. Let V and W be vector spaces over F of dimensions m and n respectively. Let V1 etc. Vm be a basis of V over F. Now let T and S be homomorphisms of V into W. Then T equals F S if and only if VIT is equal to VIS. Now if V belongs to capital V, then V can be uniquely written in this way. Now first we will assume that VIT is equal to VIS and prove that T is equal to S. Because once you have T is equal to S, this one is true. VT is equal to VS for every V. So in particular it will be true for this element VI, where I ranges from 1 to m. So, so our job is now to prove this part, which is VIT is equal to VIS. That is T and S, they agree on the basis elements, means the mappings are, the homomorphisms are equal. So you consider VT, V you can replace it by this, because T is a homomorphism, you have this step. But each V1T can be replaced by V1S, V2S and so on Vns because of this. And so if we name, okay, this here it is named as 1. So using that we have this step. And now again, as S is a homomorphism, we can take that S out. So we have, this is nothing but V, this is nothing but V. So Vt is equal to Vs we have. So this is true for every V in capital V. And therefore we have the image is equal, therefore mappings must be equal. So converse part, it's very obvious for every V. In particular we have this. Now we'll go to the main proof. What is our aim? We have whom W. We have to show that whom W is of dimension mn, which means we have to produce a basis in whom W which has got mn number of elements which are linearly independent and which span whom W. So these two we need to establish. So for which we have to define, we are going to construct those elements in whom W. So how they are constructed? You consider small v in capital V, then V in capital V can be uniquely written as lambda v1 and so on lambda mvm, where lambda is from capital F. You define your Tij from V to W by V Tij. V is nothing but this. Tij is lambda I Wj. So how this is defined? You have lambda I Vi. Okay, so that means when you have this suffix and the first suffix to be the same, this one will function. Okay, so that is how the mapping is defined. What is done to this lambda? Nothing is done. That is kept as such. But what happens to your Vi? That becomes Wj. So that is the job of my Tij. See, for example, if I consider say T1, 1, how will it take these elements? See, when we consider this lambda 1 V1, here this 1 and 1. So only when you have these two to be the same, this one will function. So what it will do, your lambda 1, it won't do anything, it will leave it as such. Then what will happen to my V1? It will change over to W1. So because of this one. Instead of this, had we had 2, then in that case we would have had lambda 1, V1, 1 and 1. That's correct. Lambda 1 will be left as such, but this V1 will change over to W2. How about the next one? See, when I consider, see, the next one is lambda 2 V2. As for the first one is concerned, as for the first one T11 we had, no? So this 2, this one and this one are not the same. The first suffix and the suffix of V, if they are not the same, then this will not take, this will not consider that element at all. So that is how my Tij is described. So you have V Tij, or rather lambda 1 V1 and so on, this lambda m Vm Tij to be only when I have this suffix and the first suffix to be the same. It will leave lambda as such and Vi will be changed over to Wj. Now having got this Tij, we are going to show that this Tij are Tijs are members of home VW, where I and J range from 1 to m and 1 to n respectively. Now to prove the claim, we have to show that Tij under addition it satisfies this, and under scalar multiplication also it satisfies the condition, the two conditions. So if V and V prime belong to V, then V and V prime can be uniquely written in this way, because V1 etc. Vm is the basis of capital V. Now you consider V plus V prime, that is your left side, here your LHS. So V plus V prime of Tij. Rewrite your V from here and V prime from here. Then collect the terms with V1, V2 and so on. Now why we write this is, we know already that only when the suffix this and this, when you consider 1 and I, they are different. M and I, they are different. So only for this it will work. So what will happen to this? Nothing will happen. So lambda I plus lambda I. And what will happen to this and the Tij? It will be taken to Wj. So by the definition of Tij, this is what we get. Now using V2 in W, all these now are members of codomain, which is W. Using V2, you have this as lambda I Wj, delta I Wj. But this is nothing but the image of V under Tij. This is nothing but image of V prime under Tij. Right. So that is my RHS. And the same way for this, you have alpha V1, alpha lambda 1 V1 and so on. This is by here your you can use your V scalar multiplication alpha U plus Vs. So V1 is used here. V1 is used here and V1 in capital V. So that is used here. Using that you have this step, and as for Tij is concerned, we will have the image only when these two are the same. What will happen to this? This is left as such. Vi, Tij will be changed to Wj. And then by V3 in W you have this step. So this is nothing but Vtij by the definition of Tij. So that's your RHS. So you have Tijs to be homomorphisms. You have Tijs to be homomorphisms. So now you consider this collection. Your I and J range from M to 1 to M, 1 to N respectively. So this is the collection, the set of all. Don't write matrix symbol. It is the flower braces that you have to write. It is set T11, T12, and so on, T1n. And so like that you have mn number of elements. Each one is a member of Hom W. Now we claim that B is a basis of Hom W. So for which we have to show that B is linearly independent in Hom W and B spans Hom W over F, of course. So in order to show that they are these vectors are linearly independent, the usual procedure, you have to consider the linear combination equate to 0. Why this big 0? Because here you have all of them to be homomorphisms, and this is not vector 0 or scalar 0. This is a 0 transformation, 0 mapping from B to W. What is the job of 0? 0 mapping. It will take any element to vector 0. So the job of this homomorphism, 0 is a vector space homomorphism. So the job of this 0, it's a mapping. In fact, homomorphism, it will take any element in V to your vector 0. This is not scalar 0, this is vector 0. So V belonging to capital V. For every V in V, you have this to happen. So you have, you are equating the linear combination to 0. Your job is to show that each scalar is 0. So you consider the linear combination equated to 0. That job is over. Now because this is a mapping, this is another mapping, homomorphism rather. This is a homomorphism, this is another homomorphism. So they must, if they are equal, means they should agree on basis elements. So for I ranging from 1 to m, Vi of this mapping, entire mapping is equal to Vi of this mapping. But we know very well that 0 homomorphism takes any vector to vector 0. This vector is vector present in W. This is the vector present in W. Now Vi of this, so we know already that it will function only when this and this are the same. Okay, so Vi, what will happen to this alpha I1? That will not be affected. So you have alpha I1, so resultant is W1. Similarly this, so this with this will only be 0 because I and 1, they are different. This suffix and this suffix should be the same. Only then this transformation, this homomorphism will function. Okay, so for all these, you will have the image of Vi under those homomorphisms to be 0. Only here we will have some value and they are given by this. So this is what we have. But we know already that W1 etc. Wn is a basis of W, and therefore the linear combination equated to the identity element in W should imply each scalar 0. Each scalar is scalar 0. So here we generalize this. Ij we are writing, your j range from 1 to n. Already my I range from 1 to m. So this shows that each of the scalars, here whatever scalar that you have considered, each one of them is 0. When you consider the linear combination equated to 0, if you get each scalar to be 0, then you have those Tij's to be linearly independent. Now for spanning part, what we do is we consider this we are going to consider. You take your S as this. Okay, alpha 1 1 T1 1, alpha 1 to T1 2 and so on. So this you have to remember. Let S be this. Now you consider T be any element in Hom W, right? Then if you are able to show that your T is nothing but S. See, S is, yes, you are considering as the linear combination of those Tij's. Linear combination of elements of B actually. If you are able to show that any arbitrary element T in Hom W is written as linear combination of elements of B, then you are through. So for that only you are taking your S as linear combination of elements of B. So this S is actually linear combination of elements of B. Your aim is to show that any element in Hom W is written as linear combination of elements of B. So for which S is first considered as linear combination of elements of B, your job is to show that any element is written as linear combination. So if you are able to show that this any element is nothing but your S, then what is required we will get. So that is the idea. So our aim now is to show that T is equal to S. To show that T is equal to S, it is enough we show that they agree on basis elements. BIT is equal to VIS. It is enough we show this. So to prove 2, we prove that T is equal to S. Now when you consider T, then VIT belonging to W, naturally, because it's a mapping from A to W. And so VIT will be, this also we are taking VIT is a member of W. So it should be written as uniquely with the help of the basis elements W1 etc. Wn in some way. But we are choosing the scalars in this way. We can have scalars, but you name the scalars as this: alpha I1, alpha I2 and so on. You can have it as say lambda 1 W1, lambda 2 W2, or even delta 1 W1, delta 2 W2 and so on. But for the convenience sake, we are naming this as this: delta 1 is named as alpha I1, delta 2 is named as alpha I2, and delta n is named as alpha In. So this part also, we see, this is what we actually need. So remembering this is not a problem, but this one you'll have to remember. And even to arrive at this, you can just leave space here, do this calculation, whatever you arrive at here, you can write it here. So in that way also you can do, but you should not forget to write it. So your VIT is a linear combination of W1 etc. Wn. The scalars are chosen in this way. Okay, so now we prove that VIT is equal to VIS. So you consider VIS, yes, already we have written, and by the definition of our TIJs, only when this and this are the same, this TIJ will function. And what will happen to this? Then nothing will happen. Alpha I1, alpha I2, they will be left as such, and this VI along with this will be W1, VI with this one will give me W2 and so on. VI with TIN will give me WN. So, but this is nothing but your VIT. In order to have this VIT on this side only, your VIT was chosen like that. So that is the reason behind choosing your scalars in this way. So this is VIT. Now again we have, this is what we claim. So LHS we have got. So this implies that S equals T. So this implies that your rather T equals S. But what is S? It's linear combination of elements of B. Linear combination of elements of B. So you have your B spanning home VW, because T is arbitrary element in home VW. So B spans, B is linearly independent, therefore B is a basis with mn number of elements, and therefore dimension of home VW. How many ever elements you have in the basis will be the dimension of home VW. So mn number of elements you have, so m into n you have, but m stands for dimension of V and n stands for dimension of W. So we have to remember this: dimension of home VW is dimension of V into dimension of W. Dimension of home VW is dimension of V into dimension of W. Now suppose we have dimension of V to be m, if we have this to be say m, then dimension of W will be, in this case we will not have W because we are asked to find dimension of home VV. So by just taking W as V, right, your W is taken as, actually W is taken as V. W is taken as V. So we get your m to be equal to n, and therefore mn becomes m squared. So dimension of home VV is m squared. Later we are going to denote this home VV as A of V. That's in chapter 6, A of V. So dimension of home VV is m square if dimension of V is m, because W is taken as V, and therefore you have this. Okay, so next we have second corollary, which states that if dimension of V is m, then dimension of home EF is m. Now how we can talk about home EF? See, we have studied about home VW, that is V is a vector space, W is another vector space. Means you have we have spoken about home VW, that is also a vector space. But we know very well that every field is a vector space over itself and over its subfield also. So here we consider our F to be a vector space over itself. F is a vector space over itself. So in the place of W, if I take F, in the place of W, if I take F, then what will happen? We will have home V F. Now dimension of home VF by this is nothing but dimension of V, dimension of V into dimension of F over itself. But dimension of F over itself is always 1. Dimension of F over itself is always 1 because any element in that will be spanned by the same element and it is linearly independent. So hence by the above theorem we get dimension of home EF to be m into 1. So you have home EF, dimension of home EF to be m. Next we have this definition of dual space. Now only comes the definition of dual space. Now home EF is also a vector space because whenever we have W to be a vector space, home EW is a vector space. In the place of W, if I replace it by F, then home EF I get. This home EF is called dual space. There is a name given to this. If you have it as some other vector space W, no name is given. But when you have it as F, then home EF is named as named as dual space, and it is denoted as, this is the notation, V cap. And its elements are called, see, we have already said that home VV, the elements in home VV which are vector space homomorphism from V to itself are called linear transformations. This is known from the first section itself, linear transformations. But when instead of V, if you have F say, then in that case home VF, which is denoted as V cap, the elements in that are called as linear functionals. They are called as linear functionals. So home EF is denoted as V cap. Now once you have V cap, see, once you have a vector space, you were able to talk about home VF, and this is what is denoted as V cap. Now having got V cap as a vector space, can we not talk about home V cap F? We need to talk about this, we need two vector spaces. Now this is named as V cap and that is a vector space known already. So we can very well talk about home V cap F. So that is denoted as V double cap and that is called the second dual space. Even that will be a vector space over the same field F, and that is called the second dual space. From corollary 2, we had dimension of home EF, that is dimension of home EF is M, means dimension of home EF is nothing but V cap. Dimension of V cap is M. So if I want to find what dimension of V double cap, what is V double cap? V double cap is nothing but home V cap F. Home V cap F. So you have dimension of V cap which is M and dimension of F which is 1. So what we conclude is dimension of V double cap is also M. Whenever M into 1, that is M only. So if you have dimension of V to be M, dimension of V cap is also M, dimension of V double cap is also M. So that is what we have in note 5. Now we will see lemma 4.3.6. If V is a finite dimensional vector space and V is a non-zero element in V, then we can find an element F in V cap. Remember, the elements in V cap are called linear functionals. So we can always find one linear functional such that the image of this V under this F is non-zero. V is non-zero, its image under F is also non-zero. Like that we can always find one linear function. So that's what this lemma says, for which we proceed like this. Let V be finite dimensional, V be a non-zero vector in V. Then by the lemma, see, we know that any set of linearly independent vectors can be extended to a basis. So here v not equal to 0, it's linearly independent. You name that as v1. So that can be extended to a basis. You assume dimension of v to be n. So we are taking dimension of v to be n. We are given v to be finite dimensional. So you take dimension of v to be n. Okay, then by lemma 4.2.1 to 4.2.21 we can find a basis of the form like this. Let vi cap be the element of v cap defined by. So let us define vi caps in this way. Vi cap of vj is 0 for I not equal to j, for I equal to j. So it is like this. v1 cap of v1 means it will be 1, whereas v1 cap of v2, okay, that will be 0. So v1 cap of v3, that will be 0, and so on. So what does it say actually? When you have the suffixes to be the same, you have the value of this, because it's a linear functional, so the values will be in f only. So either you have you will not have again a vector. So in this case you are defining your vi caps in such a way that it's either 1 or 0. When it will take the value 1, when the suffixes are the same, value is 1. So similarly, if you consider v2 cap, how that is defined? v2 cap of v1, because the suffixes are different, according to the definition it should be 0, whereas v2 cap of v2 will be 1. So when the suffixes are the suffixes are the same, the value is 1. So that's what this one is. This is the meaning. Okay, vi cap of vj is 0 for I not equal to j, and vi cap of vi, not vj, vi cap of vi is 1. Or you can say, see, suppose you are having it as vi cap of vj, then here you have to write for I equal to j. For I equal to j. So that's missing. Otherwise you can have otherwise. Okay, so vi cap of so general element when we consider, so what will be the image? Lambda I, because only when these two are the same, this one will function. So you have vi cap of vi is 1, for the rest it becomes 0, and therefore you are left with lambda I. Now in fact vi cap are nothing but the Tij's introduced in the proof of what we had in the theorem 4.3.2. So it is this Tij is nothing but our vi is what we are defining here. Okay, and w there we had, here instead you have it as f, which is one dimensional. Thus we have v1 cap and so on, vn cap form a basis called dual basis. So there we prove Tij's to be a basis. No, it is on the same line. If we proceed, we will get our v1 cap and so on, vn cap to form a basis of v cap. Okay, so thus there is an element in v cap, namely v1 cap, such that v1 cap of v, you take v1 cap and in the place of v you have v1. Okay, so v1 cap of v1, we know pretty well it is non-zero. So we are able to have by taking a v1 cap as f, and this v1 as v, f of v not equal to 0. So thing is, dual basis is used here to establish the lemma. Dual basis is considered. What is dual basis? The dual space as a basis. Whenever dimension of v is n, we know very well that dimension of v cap is also n, dimension of v double cap is also n. So when I consider v1, small v1, etc., small vn to be basis elements of capital V, correspondingly what he says is v1 cap, v2 cap and so on, vn cap will be basis elements of your v double cap. And so we in this lemma, it's enough we talk about only these two. Okay, so my f, when I take my v1 cap as f and v as v1, we are able to have f of v to be not equal to 0. That's by the definition of vi caps. Okay, Next we have this lemma. This is 5 marks question. This dimension of home VW is m into n is section C question. That is section C question, and this is section B question. This one they have asked, and even this is a section B question, and even annihilator of W, that what we are going to have. This definition can be asked in section A, and this proof that dimension of A of W is equal to this can be asked in 10, that is section C. And this is a repeated question, corollary to the theorem A annihilator of W is equal to W. That's section B. Okay, so we have now we will prove this lemma 4.3.7. If V is finite dimensional, then psi is an isomorphism of V onto V double cap. That is psi from we can always define a mapping. So what does it say is we can always define a mapping V from V to V double cap with the help of this mapping, say psi. Then we can have the psi to be 1-to-1 onto homomorphism. Okay, so V, or in other words, V is isomorphic to V double cap, which means any element in V can be regarded, if I consider V to be a member of capital V, then it can be regarded as a member of V double cap also. Now V double cap, how are the elements defined in V double cap? Home V cap of home V cap F is V double cap. So the elements of V double cap are set of all T suffix V. It is T suffix V. Don't write like this TV. So it is T suffix V. It is a mapping from V cap to F, because this is V cap to F. So V cap to F we have. How it is defined? TV of any element here is a linear functional. That's why F you have written. TV of F is equal to F of V for every F in V cap. So this is the definition of V double cap. This is the definition. This is called the second dual space. You call this V cap as just a dual space, not first dual space, just dual space, and this one is second dual space. Okay, so V double cap. So what he says is you can always regard your small v in capital V as capital T suffix V, T suffix V. So that is what this lemma says. So you define a mapping like this: psi of V is equal to T suffix V for every V in V. Then we are going to prove that psi is well defined, 1-to-1, onto, and homomorphism. Of course, vector space homomorphism. So you assume V to be equal to V prime. Because F is well defined, you have F of V is equal to F of V prime for every F, and F of V is nothing but you have the definition of F of V, that is TV of F. So this is TV prime of F, TV prime of F for every F in V cap. This you are writing, retaining as such. So TV of F, but images are equal, and therefore mappings must be equal. That is the definition of equality of mappings. We are using the definition of equality of mappings. Two mappings are equal if and only if the images are equal. Equality of mappings. So this is nothing but psi of V, this is nothing but psi of V prime. Psi is obviously onto, because V double cap, how are we defined our V double cap? Set of all TVs. So that is what you have, the elements in V double cap, and what you have written on the right side. If they are the same psi, you can say it is obviously onto. Right, to prove homomorphism, we have to check these two conditions, one with respect to addition, the other one with respect to scalar multiplication. So you consider now this, with this directly we cannot proceed, because this stands for T suffix V plus V prime. It's a mapping, V plus T suffix v plus v prime is a mapping. Unless it acts on some element, it does not have any meaning. So that is why we are considering t suffix v plus v prime of f by the definition of v double cap, which is the collection of all tv's from v tv's from v cap to f, such that tv of f, that is how it is defined, tv of f is equal to f of v for every f in f of v for every f in v cap. So this is the definition of v double cap. So t suffix v plus f v dash of f is, by this definition, is f of v plus v dash. But f is linear functional, means it's a homomorphism from v to f. So you can rewrite like this, but f of v again is nothing but tv of f. So this is tv prime of f, and by the definition of addition in v double cap, because in home vw pointwise addition is the operation, and in the same way home vf pointwise addition, again in the same way home v cap f pointwise addition. So by the definition of addition in v double cap, we can rewrite like this. So if the images are equal, therefore mappings must be equal. So t suffix v plus v prime should be equal to tv plus tv prime. But this is nothing but psi of v plus v prime, and this is psi of v, and this is psi of v prime. So this cannot be directly proved. So we'll have to, this means only this. You don't have this. So in order to speak further about this, you will have to consider t suffix v plus v prime of f. Otherwise, with just mapping, consider f means what to consider. So it's something like that. D by dx, does it have any meaning unless it acts on some function? So it's an operator. Okay, so here operator, it's a function. So you have in the same way, if you simply have t suffix v plus v prime, nothing could be done. So it has to act on some element. So that is why we consider all this. Now in the same way, t suffix alpha v of f, which is f of alpha v by this definition, and f is linear functional. So alpha comes out, and this is nothing but tv of f, and by the definition of, again, scalar multiplication. Here you have mentioned by the definition of addition in v double cap. So here it is by the definition of scalar multiplication in v double cap. So you have this step. So t suffix alpha v is alpha t suffix v. But this is nothing but psi of alpha v, and this is alpha psi of v. So psi is a homomorphism. So the psi from v to v double cap is an one-to-one onto homomorphism, therefore v is isomorphic to v double cap. Next we have the definition of annihilator of subspace of a vector space V. So if W is a subspace of V, then the annihilator of W is all those linear functionals which annihilates all the elements of W is your annihilator of W. So in that's in words that we say all those linear functionals which annihilates all the elements of W is called annihilator of W. But in notation it is this: all those linear functionals which annihilates all the elements of W is called annihilator of W.